Well, thanks everyone for joining us this Friday morning for our annual Norwood Award presentation. It's my honor as the chair of the department to present both, welcome everyone here for the award, but also present the Catholi Award. And I will do that first and then hand it over to Dr. Charity Morgan for the Norwood Award presentation. So it is my distinct honor as chair of the Department of Biostatistics, and I should have mentioned to those of you that don't know me, I'm Jeff Sikowski, I am the chair. But it is my pleasure as chair to present the Charles R. Catholi Distinguished Dissertation Award. This award is named in honor of Dr. Catholi, and with it we recognize an outstanding graduate of our doctoral programs. For those of you who know Dr. Catholi, you likely already know the positive things to follow, but I'll remind you. And to our new students and invited guests, allow me to introduce you. For many years, Dr. Catholi has dedicated himself to excellence in educating generations of biostatisticians. He joined the faculty at UAB in 1970, and since then has seen the evolution of the department, advised several students and faculty, served as department chair, and was named Professor Emeritus in 2003. In addition, he is our resident historian and is actively working to record the department's proud accomplishments and activities. He has had lasting impact on the many people he has encountered during his time here. Dr. Catholi has taught numerous courses for the department and continues to be active in the classroom. He is a benevolent and accessible advisor to his students and to his colleagues, and his dedication to the department has no end. I am fortunate to call Chuck Catholi a friend, and I encourage everyone to stop by his office and get to know him if you have not already. He always has great insight into professional and personal matters, and I am truly honored to be presenting an award that honors such a great educator, mentor, and friend. So please, everyone, give Dr. Catholi a round of applause. Sorry, I know you don't like the spotlight being thrust upon you, but I had to recognize you. This year's recipient of the Charles R. Catholi Distinguished Dissertation Award is Dr. Andrew Sims. Andrew's dissertation research is truly remarkable and is a testament to the strength of our students, our academic program, and importantly, his research advisor and advising committee. So I'm going to say a few words about Andrew. Dr. Andrew Sims, the 2023 recipient of the Charles R. Catholi Distinguished Dissertation Award, defended his dissertation in June of this year. Andrew earned his Bachelor of Science in Applied Mathematics and Scientific Computation from UAB in 2017. He then joined the Department of Biostatistics and earned his master's in 2020. He subsequently joined the PhD program and has excelled throughout his studies. While a graduate student, Andrew served as a graduate research assistant and worked on a project examining racial and socioeconomic differences in chronic low back pain. He also received a highly coveted T32 pre-doctoral fellowship. With a focus on cardiovascular disease, Andrew worked with the REGARD study team. Because of his tremendous efforts as a student, Andrew has contributed to a dozen abstracts and presentations at professional meetings. He has co-authored 8 peer-reviewed manuscripts in print, and he has quite a few additional manuscripts under review or in preparation, including works from his dissertation. Andrew's research advisor is Dr. Leanne Long, and his dissertation title is Mediation Analysis Using Marginalized Zero-Inflated Poisson Model. I want to briefly summarize his dissertation, and forgive me in advance for overly simplifying and hopefully not misrepresenting what you've done. So briefly, Andrew's research focuses on the underdeveloped area of mediation analysis with zero-inflated count variables using a counterfactual approach. With his work, mediation effects are estimated using a marginalized zero-inflated Poisson model, or MZIP model. Zero-inflated mediators and outcomes are evaluated, And importantly, his dissertation includes the development of a software package in R for performing the proposed analyses. And a few other things to note about Andrew and his accomplishments as a student before I present the award. He presented his research at the 2022 and 2023 joint statistical meetings, as well as the 2023 ENAR meeting. He also presented his research at the 2023 meeting of the Alabama-Mississippi chapter of the American Statistical Association, and he won second place in that poster competition. Finally, he is the founder and first president of the Biostatistics Student Organization at UAB. He served as the student representative on the graduate program committee, and has assisted with efforts to recruit new students into our graduate programs. All very, very well-deserved and appreciated accomplishments. So please join me in congratulating Dr. Andrew Sims for his exemplary doctoral dissertation work and remarkable accomplishments as a graduate student. Thank you. Thanks, Andrew. Okay. Next, I will turn over the floor to Dr. Charity Morgan for the presentation of the Norwood Award.
So I am Dr. Charity Morgan. I'm an associate professor here in the department, and I am the head of the Norwood Selection Committee. Before we present this year's recipient of the Norwood Award, I'd like to tell you a little bit about who Janet Norwood was and why we have honored her with this award since 2002. Janet Norwood was appointed to the U.S. Bureau of Labor Statistics by Jimmy Carter in 1979, when she became the first female commissioner of the Bureau. She headed this agency for 13 years and served under 4 U.S. presidents. She testified 137 times before Congress. She stood up to presidents, and she had a reputation for being objective, methodical, and unflappable. She once said, "I believe strongly that an objective, scientifically created system of data is essential for democracy to flourish." At the Bureau of Labor Statistics, she oversaw almost 3,000 employees, championed them and encouraging them to conduct independent research, creating what she called a cognitive laboratory within the Bureau. She once said, "What I always tried to do was to get people to do what I thought they ought to be doing because they wanted to do this." Janet Norwood embodied the principles of statistical science. She developed the Quarterly Employment Cost Index and advocated for the use of social and behavioral science in defining economic indicators. She had a particular interest in the measurement of race in the U.S. Census and the implications of undercounting racial and ethnic minorities. Janet Norwood was once quoted as saying, "We are responsible for some of the most sensitive of economic data. These data figure very prominently in most of the political debates, so it is extremely important that they be accurate and of high quality." She knew that as statisticians, our work has the potential to change the world, and she understood the importance of objectivity and statistical rigor. Janet Norwood was a fellow of the American Statistical Association and an honorary fellow of the Royal Statistical Society. In 2015, she was inducted into the Department of Labor's Hall of Honor, and the conference center at the Bureau of Labor Statistics was renamed for her at that time. She passed away in 2015 at the age of 91. The UAB Department of Biostatistics gives this award each year to not only recognize Dr. Norwood's achievements, but to recognize the contribution of all women to statistical sciences. With that being said, it's my pleasure to introduce the recipient of this year's award, Dr. Amita Manatunga. Dr. Manatunga comes to us from Emory University, where she is a Donna Jean Brogan Professor in the Rollins School of Public Health's Department of Biostatistics and Bioinformatics. Dr. Manatunga received a bachelor's degree in physics and mathematics and a diploma in applied statistics from the University of Colombo in Sri Lanka, a master's in mathematical statistics from Purdue, and a master's and PhD in statistics from the University of Rochester. Her career began as an assistant professor in the Division of Biostatistics at Indiana University before she joined the Emory faculty as assistant professor in 1994. She rose through the ranks at Emory, becoming an associate professor in 1997, then full professor in 2004. In 2020, she was named the first Donna J. Brogan Professor of Biostatistics, which is one of only 2 named professorships in the history of the department. And we're also lucky to have Dr. Brogan here with us today as well. Dr. Manatunga's research interests include prediction and estimation with complex functional data. She has authored or co-authored over 130 peer-reviewed publications. She has maintained a consistent track record of NIH funding and regularly serves on review panels as a methodological expert. We are not the first to recognize Dr. Manatunga's achievements. She is an ASA Fellow and has received the Rollins School of Public Health's Thomas Sellers Award and the ASA's Elizabeth Scott Award. Among her many accomplishments, Dr. Manatunga stands out for her mentorship of the current and future generations of statistical leadership. She chairs the Committee of Presidents of Statistical Societies. She co-founded the ENAR Diversity Workshop. Both of the current presidents of the ASA and ENAR were mentored by her. And she was also one of the postdoctoral advisors for our own Dr. Fazli Rahman as well. In 2020, she was recognized for her outstanding mentorship with the Emory University Women of Excellence Award. Please join me in welcoming Dr. Manatunga.
Thank you to the award committee. Thank you, Charity, and a very generous introduction. It is an amazing honor, and I am honored and humbled to receive this award and to be associated with this honor in the name of Janet Norwood. She was a trailblazer for our profession. She was a magnificent statistician, mentor, and inspirational model to many of us. So I want to express my deepest gratitude to those who made it possible for me to receive this award and the lectureship. I consider myself to be someone who beat all odds. Growing up in a small village in Sri Lanka, living under poverty, arriving in the United States, working in academia at Emory, and receiving this important recognition from the University of Alabama in the name of Janet Norwood. I consider this recognition to be of great significance. I want to acknowledge my colleagues at Emory, my nominator Lance Waller, and my mentor Donna Brogan, who is here, and my colleague Ying Guo for their continuous support throughout my career. I also want to thank my family and my husband and for his generous continuing support. Finally, I would like to dedicate this award to the memory of my mother, who taught me how to be strong, independent, and to always serve others. Thank you. I'm going to talk about predictive models for complex data in biostatistics and data science. And so again, I want to say thank you, from my own experience. I know organizing activities as these takes a lot of effort from lots of people, So I know this lecture is a result of multiple people's hard work, And I also want to thank David Allison and others for establishing this award. So I want to thank all of you inviting me to give this lecture. And thank you for coming. So let me first start saying that Dr. Norwood is an amazing woman. And she is an inspirational model to many, many women. And her extraordinary service to the government is incredible. And she believes so much objectivity of data. And she said, as Charity said before, I believe strongly that an objective, scientifically created system of data is essential for a democracy to flourish. What a beautiful statement. The value of such wisdom and thinking must be appreciated and recognized. And as statisticians, we all see the value and can very well appreciate it. She was a strong advocate for the equality for women. We are the beneficiaries from her contributions. So to move on, let me just say that I am very, very grateful to receive this award in the name of Janet Norwood, a giant in our profession who is a magnificent role model and a mentor. Speaking of mentors, and I would like to start my presentation expressing my deepest gratitude to my own mentors. Dana Brogan, actually I didn't expect her to come here, but she drove all the way from Atlanta, and Professor of Emerita of Biostatistics at Emory, another distinguished woman who fought for the equality for women. Dana is the founder of the Caucus of Women in Statistics at the ASA, American Statistical Association. Dana worked very hard to promote women to academia. She recruited me to Emory, and one of 6 women she recruited at that time, and she always supported my career. So I also want to acknowledge my dissertation advisor, David Oakes, Professor of Statistics at the University of Rochester. I learned a great deal from him. Late Professor V.K. Samaranayake, a Professor of Mathematics from University of Colombo, Sri Lanka, is the one who introduced me to joy of statistics, for which I am very, very grateful. In a time like this, I really would like to acknowledge all of their contributions to promote my career. I know you heard the introduction of me, but when you come from a small island, it is important for me to say where I am from. So I was born in Sri Lanka and earned my bachelor's degree from University of Colombo. This is an independent country located at the south of India. And I got to know about statistics through diploma in applied statistics, and I received it from University of Colombo. Later came to this country to do my PhD and earning a master's degree from Purdue University, and then I transferred to University of Rochester and received my master's degree and the bachelor's degree. I am going to talk to you today about my research work and my experience as a biostatistician. So this slide shows a summary of my current engagements. I have 30 years of collaborating with biomedical scientists, and I also currently I am the primary statistician for 2 clinical trials, and the first one is evaluating a drug in reducing exposure of PBB, some chemical called PBB, among reproductive women. And I am also engaged in another trial, evaluation of the effectiveness of an intervention encouraging to establish living will for advanced stage patients in dialysis clinics. I am also engaged in statistical methodology research, and I have a mental health research group, and predictive modeling is what I am going to talk about today. And I also do training and having PhD students. So I have highlighted here the last line, mentoring junior faculty, clinical researchers, and PhD students. Currently, I am heavily engaged in mentoring activities. These activities are very meaningful to me and rewarding as well. So this is the layout of my presentation today. I have organized my presentation into 2 parts. The first part relates to the topic of thriving our profession, and I will take few minutes to talk about some successful programs based on my own experience. The second part is focused on prediction. I will describe 2 studies. I'm going to focus on scientific aspect of those studies. I'm not going to talk about technical aspects of modeling, and hope you are not disappointed, which is not the focus on my talk today. I will make some remarks again based on my experience about data science and biostatistics. So let me start with thriving our profession. About 20 years ago, I co-founded INA Diversity Workplace with Louis Ryan. The goal was to increase the representation of minority groups in the field of biostatistics, to increase recruitment, retention, and promotion of underrepresented groups in the field of biostatistics, and was sponsored by East North American region of International Biostatistics Society, INA. And on the right-hand side, this is the agenda of the very first INA diversity workshop. And it was on Sunday and Palmer House on Chicago, Illinois. And Louis Ryan gave the welcome speech, and then the keynote speaker was Bill Jenkins. Some of you may know who Bill Jenkins is, and Bill Jenkins is a biomedical researcher at the CDC. He and others worked very, very hard to stop the Tuskegee study of syphilis among untreated African men. Unfortunately, he passed away 4 years ago, and he had been a mentor to many, many African American students from Georgia State, Emory, Georgia Tech, and Morehouse. You can also see here in the agenda the Du Bois Bowman as a young faculty participating in a panel in which I am the moderator. And he is currently the Dean of School of Public Health at the University of Michigan. So we are very, very happy for him. And today, in our diversity workshop has around 100 participants, and it is very, very popular, and you could see from the picture. And I'm not an organizer anymore, but I am amazed by this success, which is happening every year for the last 23 years. What worked? The one thing worked was the leadership of Louis Ryan and her vision at the very beginning. And I was just following her direction at that time as an assistant professor. And we always found very motivated, enthusiastic organizers who are focused and cared about a common goal. And we were able to pass the torch to new generations every year. It is just amazing. And so I want to say, this is a great opportunity for young leaders. And as a very young assistant professor, I had the opportunity to work with Louis. This opened up so many opportunities for me, networking with lots of people. This is not something I planned, but it just happened. And another example, as Charity said, 2 of my PhD students also led this workshop, and they are actually, became presidents later. Dion Price is the current ASA president, and Renee Moore is the INA president, current INA president, and I'm very, very proud of them. So I'm not here to talk about me. I want to show you what you can accomplish at very young age. And I encourage all of you to engage in our profession and choose tasks or activities that are meaningful to you. Remember, more you give, more you get. So under my first topic of thriving in our profession, I am going to talk about team science or organizational team building. Again, I am going to speak about based on my experience at Emory. About 18 years ago, I established a mental health research group at the Department of Biostatistics and Bioinformatics at Emory. So this is the leading sentence in a new article about our group, appeared in 2019 under the title Trio in Biostatistics and Role Model for All. And long-lived collaborations in academia area and successful female researchers in statistical and math sciences are far from commonplace. To my left, Ying Guo, one of my colleagues, and to the right, the Limin Peng, who is also a colleague of mine at Emory. The goal is to develop quantitative methods suitable for mental health research and provide training and promote quantitative skills to have direct impact on public health and the well-being of our society. 3 of us are biostatisticians, but we bring different expertise to the table. Ying is an expert in neuroimaging, and I have done lots of collaboration with mental health research studies, and Limin is a leading researcher with a very strong theory background. And there is also something common to us, and of course, we all are women. And it happened to be that, coincidentally, all 3 of us trained in survival analysis for our PhD dissertation. And then we also have 2 other women in a women group, and Jennifer Stevens, neuroscientist, and Tanya Jovanovich, and neuropsychology. We have been working 18 years together. As you see here, the first application, R01 application, I was the principal investigator. And later on, and then they all became principal investigators as well under the multiple principal investigator mechanism. And we have been funded by the National Institute of Mental Health for last 18 years. So I wanted to share this success story with you. And actually, Fassler, who is a faculty member here and just promoted to associate professor, he was a postdoc in this grant. And I wanted to share this success story with you. This is one way to organize your research agenda and succeed. To create groups with complementary strengths who can work together. It can be lots of fun. So let me get back to the prediction models in multiple research and multidisciplinary research. And the current environment for statisticians is very exciting. We are in a very, very hot field. Data collection methods are progressing at a very, very fast pace. As the data collections continues to grow, the question of researchers ask about the data are becoming increasingly complex. Is it possible to identify individuals prior to the development of Alzheimer's disease? This study is called Emory Healthy Aging Study. It collects data regarding neuroimaging biomarkers, various omics, cognitive functions. It is very challenging to design such a study. One has to make sure enough subjects will develop Alzheimer's at the end of the follow-up period. So, and another question is mental health there is a huge overlap between different mental health diseases. So what are the new ways of classifying mental disorders based on dimension of observable behavior and neurobiological measures? So the strategy is to conduct a classification system for diagnosis based on genetics, neuroscience, and cognitive science. Data are becoming increasingly complex, and data generated from different modalities, images, smartphones, social media, and also as statisticians, we are used to reading rectangular data, rows and columns, right? But now the data comes as not only scalars and vectors, matrices, tensors, etc. Typically, these data are very, very large and called big data. And so I need to say something about data science. So technology advancements, massive data collections, fast computers, and computational supremacy, all these things, with all these things, data science field has emerged. Consequently, there are many data scientists and training programs for data scientists. very hot field. Most training programs are housed in computer science departments. So this begs the question of what is data science? And it is really difficult to find out what is. There is really no clean definition, but at least we can come to terms with saying that it is some combination of statistics and computer science. So, and these two sayings, I took it from Rice University, Department of Computer Science, under their blocks, and it says, and as professionals and skill areas, both work field and raw data, and then seek to convert that data into insights, both meaning statistics and data science. The main difference between them is the data scientists must understand and employ graduate level statistics, computer science, and programming in their work, whereas statisticians generally have strong math skills and are not educated in computer science. Okay, a little bit condescending, right? And then the statistical modeling required statistics and data science does overlap, but statistics doesn't require the sophistication of computational tools and programming and by data science to manage the data. And so that might be true. So I took this from the stat guy from Facebook, okay? So from the late night show, Jimmy Fallon and Jennifer Lawrence are talking to each other and asking what is the difference between statistics and data science. And the answer is statistics is the mother, data science is one of children, right? So Mo sounds like a spoiled child, right? Not being able to give credit to the mother. So the common theme you hear from data scientists is data scientists do predictions, but statisticians test hypotheses and give p-values. And statisticians work on problems with small samples. I'm not saying all data scientists are all experts in machine learning are saying this. I'm sure there are highly qualified machine learning researchers recognize the value of statistics. But this is quite common. And this is another cartoon from a stat guy from Facebook and Twitter. And it says, when you're fundraising, it is AI. When you're hiring, it is ML, machine learning. When you are implementing, it is just logistic regression, right? So in fact, data scientists do often use logistic regression. So now let me go back to statistics, and I would highly recommend David Donahoe's 50 Years of Data Science. This is a very good landmark study, landmark paper on the subject of data science. And Marie Davidian also wrote in Amstrad News, aren't we, meaning statisticians, doing data science already? You know? So the following is taken from Leo Breeman's Two Cultures data, and it talks about what statisticians do. Statistics starts with data. Think of data as being generated by a black box with a vector of input variables x, and then on the other side, the response variable y come out. Inside the black box, nature functions to associate the predictor variables with the response variables. And there are two goals in analyzing data. One is to be able to predict what responses are going to be future with the input variables. The second one is to infer how nature is associating the response variables and input variables. So most statisticians actually focus on the second, to find out how the variables are associated with the response variable. So now I want to go back to my own work and my experience as a biostatistician in prediction. And so in prediction, it is important to formulate a sensible model. This requires in-depth of understanding about the problem, particularly how data is generated. And I'm going to talk about two studies that I had worked and were currently working, and I am particularly going to show you how the data is generated and what is important. And the first one is this is my project one. It is to develop a decision supporting system to predict kidney obstruction interpretation based on renogram curve data from renal images and other clinical variables. And this was a grant funded 5 years ago, and also some RO1 from my colleague Andrew Taylor, who is a nuclear medicine specialist. So what is kidney obstruction? It is obstructions to the kidney. You see a picture of kidney on the right-hand side. So resistance to urine outflow from the kidney that left untreated will result in loss of renal function. So if it is not treated, when the obstruction happens, there can be very bad consequences, meaning the dialysis or possibly even transplantation. So dialysis radiography is a widely available non-invasive test that can evaluate renal function. And basically the idea is the radioactive agent is called MAG3 is injected to the patients, and then the patient goes through this gamma camera. And this exposure for the radioactive agent is very, very minimal. And so then the series of images are taken with this camera, and then the radiologists, they do review all these images and the data, and they interpret the kidney as obstructed, non-obstructed, or equivocal. And if the patient is obstructed, the patient is sent to the surgeon for operation, but if it is equivocal or non-obstructed, patient is put under observation. So these are the images taken for every 20 seconds for 20 minutes. And here, these images are transformed to curve called renogram curve. So the principle is pretty easy. So you could see normal people have 2 kidneys. So you see the 2 kidneys, and the bladder is here at the bottom. So the first picture, you could see the bladder is on the bottom. You could hardly see it is because it is white. So there are 2 kidneys. So radioactive agent is absorbed, so it becomes black. And over the images, over the images, the bladder actually becomes blacks at the end, because if the kidney is normal, usually over time it gets rid of the radioactive agent, but if the kidney is obstructed, basically it doesn't. Because if you see the very last picture, the right kidney is a little bit black, showing that it might be obstructed, And so these images are transferred to a curve, and basically they draw a background around the kidney and calculate the photon counts in those kidneys, and then translate it to a point on a curve, and so this is how it goes. So you could see in this curve, the radioactive agent is absorbed at the beginning very fast, within the few seconds, and then it goes to a maximum, and then it eliminates the agent because this kidney is non-obstructed. So these are the images or the pictures that the radiologists review. And they look at these pictures it has images, and it also has, you could see there are 2 curves in one plot. That means for 2 kidneys. But there are also another plot because they consider 2 backgrounds. One background is called whole kidney, the other background is called cortical kidney. So they review these images, clinical variables, and history, and these called renogram curves, and classify them obstructed or non-obstructed. So these are 3 patients with a very clean view, and it is not the case for many patients. You could see the black curve is non-obstructed. It eliminates the radioactive agent very fast. and the red one is obstructed, it stays on the top. So this is an unfortunate case because it doesn't come down, the red case, the kidney is obstructed, and at the same time you are kind of stuck with this radioactive agent, but it is nothing to worry because the exposure is quite minimal. So the green curve actually is the equivocal, meaning they cannot really say it, whether it is the obstructed or non-obstructed. So why is this problem important? It is important because diagnosis of kidney obstruction based on renal images is a difficult problem. And in current practice, misclassification of obstruction is quite common. And there is a very high variability in renogram curves from different groups, So they can be very, very variable. And the main issue is the low volume studies. And they receive, radiologists receive very limited training. The reason for this is the cardiac images. Many people have cardiac problems, it is highly prevalent. On the other hand, there are only few people have kidney images. So radiologists take a lot of time to train in cardiac images. But something like kidney images, they get only very limited training. So they make mistakes, And experts also do not always agree, about only 95% of the time. So this is the possible solution, develop a decision supporting system to assist radiologists. But we are not trying to replace the radiologist, basically giving another opinion. This patient is coming to the doctor and was told that has an obstruction, and then she is asking, doctor, can you ask the computer, So, you could help me. So that is the basic idea. So let me say what the data is and the challenges. The first challenge is no gold standard in obstruction of interpretation. So you could see left-hand panel is the data from the patient. They also do 2 images for each patient. The reason they do 2 images is to exclude dehydration, because sometimes dehydration with the dehydration, it's hard for them to say from the first curve. So in this study, what we did was we collected all the images, and all these images were interpreted by 3 experts, and Andrew Taylor and Dr. Harker from Emory, and Eva Dubowski from University of Alabama. And Eva actually, unfortunately, passed away early this year. She has been a great collaborator. I think she worked with us almost last 15, 18 years and published numerous papers, and we dearly miss her. So the data actually, in terms of statistics, what we have, the data is renogram curves and numerous characteristics, clinical variables, and the expert opinions. So this is the only slide I have equations, okay? So hope you are not disappointed. So this is the likelihood basically. So the likelihood, left-hand side, you see we have the expert ratings, and it represents the expert's opinion about the kidney, and we have 3 experts, and obstructed, non-obstructed, and equivocal. And the right-hand side, we have the renogram curve, and the renogram curve, so we proposed a latent model. So meaning we are thinking the obstruction status is unobserved, which is a latent variable, and that produces the clinical variables, and in this picture, and then also the renogram curves that inform the renogram curves and the expert opinions. Okay, so that is the model, and we use MCMC to implement this model and get the results, So how do we evaluate the predictive models? So usually when people evaluate predictive models, you have a test data set. You apply your model, and then you see the observed versus predicted, But how do we do that? Because the performance when there is no gold standard, what we have is 3 experts. So what we do is, because there is no gold standard, And for the test data set, we treat the ratings as missing data, and we use the marginal likelihood to do the prediction, So in our algorithm, we propose two predictions. One prediction is only based on patient's data, patient's information. And the other prediction, we adjust the prediction when there is a radiologist sitting there. Given the radiologist's response, we adjust our response. So this work was published in JASA in 2022, JASA applications. And then you could see here the results. So in the results, the first row is the prediction only based on the algorithm. And the second row is the prediction in the presence of an expert. And then it is hard to compare to the, as we know, to the, because we don't have a gold standard. So we have 3 experts, and we did k-means and functional. And so you could see here our accuracy is pretty good. And we also have observed versus predicted curves for 2 patients. They seems to predict pretty well. I know you don't want to hear another project, but I have to say this because this is a project that I am working currently. And so I like to hear if you have some ideas as well. So this is a second project I have, and it is to develop a new image analysis algorithm that analyzes clinical pallor in fingernail photos to enable prediction of hemoglobin level for anemia risk among very low birth weight infants. And this was a RO1 funded by me, and for me last 2 years ago. And also there is a PO1 project with Dr. Cassandra Josephson. So this is how the story begins. And Dr. Manino from Georgia Tech, and actually he was a PhD student at that time, he developed a smartphone app for non-invasive detection of anemia based on the color of the fingernail bed, and to predict the anemia status. And so the idea is you take a picture from the smartphone and of your fingernail, and then that translates into data, and he analyzed this data based on weighted robust regression model. It is a very simple model he did. He basically averaged all the data, all the red, green, and blue, and then do the weighted robust regression model to predict the hemoglobin status. And then he showed that the y-axis is the smartphone prediction, and x-axis the true hemoglobin level. And then he showed that actually clinical color in your fingernail can be associated with the hemoglobin level. And clearly, the green ones are the control, healthy people, and then the red ones and the other ones are people who have problems with anemia. So it has some separation power. So what we want to do is, we want to see whether his smartphone first, whether it does a good job and predicting hemoglobin level for low birth weight infants. Okay? So what is the data? So data is basically, in this picture you could see it is a photo, and we have 3 matrices, and the matrices are red, green, and blue 52 by 52 matrices. So that is what the data is. So why is it important, this problem? So because this problem is important, first of all, they are preterm low birth weight infants, and they usually are monitored about 6-7 weeks at the hospital for anemia and for other complications. And the blood is drawn over time to measure the hemoglobin level. And so when babies are at risk for anemia, they receive red blood transfusions. So these arrows indicates over time, at the beginning actually their hemoglobin level is pretty high, but then they lose the hemoglobin level, and then these arrows indicate when they get the blood transfusions, And so our goal here is to see whether we can minimize the blood drawings, because drawing blood from the babies who are at risk for anemia is counterproductive. And also, drawing blood has other adverse health consequences for babies. So what we try to do is we try to develop a predictive algorithm to leverage longitudinal patient-level clinical data and color images to achieving the overreaching goal of minimizing the number of blood draws throughout the care for continuum among VLBL patients. And as you know, this is a very vulnerable the group of patients. So the idea is maybe we can replace some of these blood draws in terms of a photo, and then looking at the photos and the blood draws, whether we can predict. So that is the question. So the left-hand side, the picture is the observed versus predicted based on the smartphone, which was developed for adults. So you could see it is quite off, because it was developed for adults. And the right-hand side was our preliminary data. We analyzed 22 patients, and then we showed that using some principal component analysis, we can get a reasonable prediction. So we are working on this problem right now, and we have only one publication just submitted, but there are lots of analytical challenges, functional, two-dimensional data. Actually, it is not even matrices, they are tensor, because we have three things, and then longitudinal and as confounding. And scientifically, this is also very challenging. What is the outcome of interest? Is it really the hemoglobin, or is it the blood transfusion? Or is it the change in level of oxygens with the blood transfusion? So there are lots of issues going on with the study. Physicians have guidelines to give blood transfusion. Usually they give transfusion based on low hemoglobin ventilation. So should we predict proxy measurements of blood transfusion? So you could see in real data analysis, in an example like this, it really is important to figure out which one you want to predict. So I want to say very few things about, in both of these studies actually, some physicists work in the renal study. They basically calculate characteristics of curve, time to maximum and all, and they use all these characteristics to define rules and have developed an algorithm. Actually, in that case, that algorithm produced reasonably good results. But we haven't compared ours to them. And then in the infant study, with the medical records, and they have done some work actually, but none of them are very successful. They came up with some DAG pictures that nobody could explain actually. So that is kind of the results did not provide insights. So within last few minutes, I know time is, I need to be, within last few minutes, I want to talk a little bit about the successes and failures. And so if you look at under successes, we were able to obtain in the renal study good accuracy. And we were quite productive. We had a JAS application paper, biometrics, biostatistics, statin menacing, and statistical methods in research. And we also had several collaborative research papers. And obviously, I got this grant that pays my salary. We are all on soft money, so that was important to me, right? But, and we also had several MPH theses, and more than anything, it was a lot of fun, So the failures is the implementation of algorithm in practice. It was not user-friendly, it was not tested, and lack of personnel to implement. So the problem was, I wouldn't say a problem, but this work was done with a postdoc, and who is an assistant professor at Indiana University right now. So he worked on the algorithm and did the paper. The issue is, our postdocs come to us to get a new faculty position. So we don't want them to write algorithms and practice algorithms and spend a lot of time, because that's not going to help them to develop their career, So that was one of the major issues, He did the algorithm, but we cannot really make it user-friendly because he cannot spend the time, And lack of reproducibility studies, we didn't compare to them. Those are the major failures. So I'm sure many of you agree statistical models are interpretable and they help understanding, confounding what variables contribute to prediction and underlies mechanism, and we can also quantify uncertainties. There are some recent work in machine learning in the right direction called interpretable machine learning. So they define interpretability is the degree to which a human can understand the cause of a decision. This was done by Miller. And for example, logistic regression and regression, they call it interpretable models. Mostly random forest support vector machines, they call it not, they are not interpretable. And then there is also work in causal inference in machine learning, and there was a YouTube in Royal Statistical Society, and that is quite interesting. So are we doing a good job, or am I doing a good job as a biostatistician in prediction? I think we are too slow, and I don't have very good training in computational methods, so it is hard to advise someone, for training. And how to compare other methods, including machine learning methods and reproducibility. Even there isn't a whole lot of good theory in reproducibility in terms of statistical theory. So based on my experience, these are some suggestions I think, and some of them are already happening. And we need to revise and update our curriculums to include more computing. And our standard curriculums lack computing courses, and they haven't changed over time. And then I also think creating new journals emphasizing the predictive methods with true data. It is really hard to develop a predictive model and then apply and evaluate and publish in a statistical journal. And there are no journals like that. And so asking a postdoc to do something is impossible, and it's not fair, because that's not really that they come to us. And also we need to revise our career advancements, promotions, tenure to recognize computational contributions. So that is, I think, if you look at this is very clear from my successes and failures. My successes are exactly matched with promotion criteria. The many promotion criteria, getting RO1 and getting those publications, they exactly match. And my failures, basically. So I think we need to think about how to revise the the curriculums as well as revise the career advancements guidelines. So I think I also want to say, in my opinion, we cannot afford to whine about data scientists, We do quite a lot of whining, not giving credit to us, as I have done today. But we need to take this as a challenge and stop whining. We should train our students and engage with these true collaborative activities and train our students. So I do think future is very bright and exciting for statisticians, and statisticians are now working on really cutting-edge inferential method, causal inference method, and recently, actually, there is accelerated growth in our users and our packages and Python, and also statistical methods are needed more than ever for big data. So finally, I want to say fundamentals matter. Meaning, properly designed studies help evaluating interventions, biomarkers, diagnosis, and they can help underline mechanisms. So I think we are at our best doing these things. And as a biostatistician, my belief is that we have a responsibility to ensure that not only research findings are accurate, but also to actively engage in scientific endeavor for enhancing science. So I want to thank, my mentors and my colleagues, and also my funding agencies. Thank you.
Dr. Manatunga, it is my pleasure to present you with the Janet Norwood Award for a distinguished outstanding achievement by a woman in statistical sciences.
Thank you. Thank you.